Okay, so we had studied motion, and we started this semester by studying motion in one dimension. Okay, and you saw that you could treat this object as a point object because every point on the object was moving, had the same displacement, had the same velocity, same acceleration, and all that. Yep. And today we'll study the following. Let's say here's a blade or a fan. Okay, I'll draw two more spokes. Okay, so here's a blade, and it's rotating like that. It's rotating about this axis. So the axis is coming out of the sheet, and it's rotating about this axis, and it's a rigid object. Okay. Now when an object is rotating, so here's the axis of rotation. You see, let's say this thing is rotating once every second. This point is traveling that distance in 1 second. This point is traveling that distance in 1 second. So the further out you are from the axis of rotation, the faster you're moving. So this motion is very different than this motion. Okay? Different points are moving different distances, their speeds are different, and so on. So first thing, now you can't treat this as a point object. Okay? And as you can see, these two seem to be very unrelated motions, right? But surprisingly, you'll find out that all the equations describing this motion are very similar to the equation describing those motions. Yeah. All right, so in this rotational motion, is there anything that is the same for every point on this object? I'm sorry?
How long it takes to do one rotation.
Right, that is a good point. Okay, so, and also, so it turns out that when this point rotates through an angle of 45 degrees, let's say, by what angle did this guy rotate? 45. Every point on the object rotated by the same angle. Okay, and that happens for a rigid object. It probably won't happen for the coffee in your cup. If you stir your coffee, every point of the coffee won't rotate through the same angle. Okay, so what we'll be studying is rotation of a rigid object about a fixed axis. Okay. All right, so let me show you this example of this. Okay, so this is a sort of in an unrelated context, and this is a generator, which you'll learn about in physics 2. Okay, so this is the object we're interested in. See, so here's a rigid object that's rotating about an axis passing through the center, perpendicular to the plane. Okay, and what you notice is every point on the object is rotating through the same angle. Okay. And so what we will be doing is, in describing the motion of this object, what were you interested in? You were interested in x as a function of time. So similarly, describing this rotational motion will involve describing the angular position as a function of time. Okay? And then you'll see that all the equations describing the motion of this object will be very similar to that. Okay, so the equation describing the motion of that object, and that's what we'll study. Okay, so essentially what you studied over 9 chapters, you'll study for rotational motion in 2 chapters. Okay. All right, so with that in mind, let's get on into the slides. Okay. So we'll look at rotational variables, angular position, velocity and acceleration, angular quantities and vectors. Moments of inertia, we'll talk about moments of inertia. So do you guys remember what is Newton's second law? F equals ma. Okay, so mass times acceleration. What Newton's second law says is if you apply a force to an object, greater its mass, smaller its acceleration. Okay? So greater the mass, smaller the acceleration. So mass is a measure of how much it's resisting change in motion. Okay? So similarly, you'll learn for rotational motion, forces cause linear acceleration. You will learn torques cause angular acceleration. Okay. And the thing that resists this angular acceleration is called moment of inertia. Okay. So moment of inertia takes the place of mass in rotational motion. Moment of inertia is denoted by I. And greater the moment of inertia, smaller the angular acceleration. Okay. The greater this is, smaller the angular acceleration. All right. For a given object, the mass is fixed. Okay? You'll see that moment of inertia for a given object can have infinitely different values, depending on what axis you calculate the moment of inertia. Okay, so the moment of inertia for an object is not unique. It depends on the axis about which you're calculating. But anyway, moment of inertia takes the place of mass. Okay, so torques cause angular acceleration. All right, this is a picture of a centrifuge. Okay, this I believe is in Houston. One of this kind of stuff is in Houston, and there's the axis of rotation. Okay, you can place astronauts there and spin this object, and you can subject astronauts up to 20 Gs. Okay, so the seat would be pushing them with a force of 20 times their weight. You know? So for instance, if you put an astronaut like this, and there's the head of the astronaut, and there's the feet, and you spin this thing, all the blood will go to the feet of the astronaut, and you can make them pass out. Yeah. So anyway, all right, so we look at rotating objects, and we have rotating objects all around us. Again, like I said, I showed you this. So this is a generator, and you'll learn about this in the next chapter. I mean, in physics 2. So you rotate a magnet, and if the magnetic field through this thing, through a coil, is changing, it'll induce a current in it. Okay, so what you're doing is the energy of the water is converted to electrical energy. You know? So that's what a generator does. It converts mechanical energy to electrical energy. All right, so here is a rotating object. Okay. So when an extended object rotates, all parts of the objects do not have the same linear velocity and acceleration. When this guy rotates, this tip is moving much faster than this point. Okay, they all don't have the same velocity. The tip is moving a longer distance. The displacement is larger than for this guy. Okay. So the motion of the object cannot be analyzed by treating it as a point particle. Okay. For this guy, you were able to treat this object as a point particle. When your car moves, when you drive your car along a straight line, you can treat your car as a point particle, even though it's not a point particle, okay? So we will look at rigid objects rotating about a fixed axis. Okay, so let me show this to you here. So here's a rigid object. So again, this is bicycle wheel. Here's a rigid object, and there's the axis of rotation. Okay, so this is what we'll consider. We won't consider this motion, that's too complicated. The axis was not fixed there. Okay? So this is what we'll consider. But it turns out that here's another motion that's fairly simple. Even though the axis is moving here, the rolling motion is fairly simple, and we'll talk about that later. And obviously, the rolling motion is important in your life. Okay. That's how you got here. Yeah. All right, so we'll talk about that. All right, so here's an object, a rigid object. It's rotating about that axis going through the center. We'll use a reference line. Just like for linear motion, you had an origin, you had an axis, okay? And you referred the position of this object with reference to that axis. Similarly, there is this reference line. Again, there is the axis of rotation. And when this object rotates, the angular position, so when the angular position is given by this angle theta. Just like here, we had adopted the convention, if you move to the right, those distances are positive and those positions are negative. Just like that. If you rotate counterclockwise, those angles are positive. Angles measured clockwise are negative. Okay. Angles will be measured in something called radians. Okay. Radians is a dimensionless quantity, and here's how it's defined. Okay, so the angle theta is given by this arc length divided by the distance from the axis of rotation. Arc length divided by the distance from the axis of rotation. Okay. That's measured in meters, that's in meters. So meters cancels meters, so theta is a dimensionless quantity. Okay. And it's given an artificial name, unit radians. So, but radians is dimensionless. Okay. A radian is dimensionless. Okay, so if this is equal to r, that will be 1 radian. If s equal to r, that will be 1 radian. And in degrees, it works out to be about, so 1 radian works out to be about 57 degrees. Okay. In a full circle, the angle for a full circle is, theta is, arc length is 2 pi r divided by r equal to 2 pi radians. Okay. Okay, so for again, everything we talk about in this chapter will give you the corresponding example for linear motion. So in linear motion, the displacement was x2 final position minus initial position. The displacement was equal to x2 minus x1, or x final minus x initial. Okay, similarly, angular displacement given by delta theta instead of delta x, delta theta is the final angular position minus the initial angular position. So if this object, imagine an object there, it was rotating, there is its initial angular position and there is the final angular position. Its angular displacement is this angle. Okay. All right, so again, here, So for this object, we are measuring its angular position with respect to that axis, x-axis, this axis. So let's say this is its initial position, and there is a final position. The angular displacement is final angular position minus initial angular position. Okay? In linear motion, the speed was displacement. Well, the velocity was displacement over time. Okay, so similarly, angular velocity, okay, is displacement divided by the time over which that happened. We were interested in the instantaneous angular. We're calling this angular speed because I've not shown you the direction yet. Okay, and so this is the magnitude of the velocity. Angular velocity is time rate of change of angular position. Okay. So let's say, so let me show you this again. So let's say I have this object rotating, and I'll do a motion. Let's say I have some crazy motion like this. Okay. If I want to describe that motion, how do I best describe that motion? To describe a motion, this angular motion. Okay, so let me remind you of, let's go back to an object traveling in a straight line. If you wanted to describe that motion, what is the best way to describe that motion? What is the most useful way to describe the motion? Position as a function of time. Okay, just like that, to describe an angular motion, what is the best way, the most useful way for me is to give the angular position as a function of time. Okay? So if I do some motion like this, and I ask you to describe the motion, what I really want you to tell me is the position of this guy as a function of time. Okay? Why? Because you guys are all calculus experts. If somebody gives you the angular position as a function of time, you can calculate its angular velocity, which is d theta by dt, 10t plus 6. And then you'll see in a second, you can calculate its angular acceleration. Angular acceleration is denoted by alpha, which is the time derivative of its angular velocity. Okay. Yeah. So once you're given this, you can calculate that, which is the angular velocity and angular acceleration. Generally, those are the things that you're interested in. Okay. All right. So that's what this is. Angular velocity is time derivative of angular position. Okay. So here is the direction of the angular velocity. Okay. If an object is rotating that way, you use your right hand, your fingers point in the direction of the rotation, and your thumb points in the direction of the velocity. So that is the direction of the angular velocity. Okay, that's the convention. Okay, so just like for linear motion, an object could either travel in this direction or that direction. The velocity had only two directions, and when it was moving in this direction, when it was moving to the right, the velocity, the direction of the velocity was indicated by the sign. Okay, this was 5 meters per second, and this was minus 3 meters per second. The sign told you the direction of the vector because there were only two directions. Just like that, for this guy, there's only two directions. The velocity points in this direction or that direction. Okay, and so if you're looking at it from this direction, if it's a counterclockwise rotation, that's taken to be positive. A clockwise rotation is taken to be negative. Okay, just a convention. All right, anyway, you use your right hand to get the direction of the velocity. Yep. When do you accelerate? When are you accelerating?
You change the angle and have a force.
All right, let's go back to this guy. For this guy to be accelerating, what needs to be happening?
Force needs to be acting on it.
Yeah, and its velocity needs to be changing. Okay, so anytime and somebody asks you a physics question, go to an equation. Okay, so what was the question? When are you accelerating? Meaning, when is this non-zero? When velocity is changing. Okay, so similarly, when do you accelerate? Angular acceleration. When angular velocity changes. Okay. All right, now for us, what did we do? We said, okay, so I'm going back to this example of this wheel rotating. Okay, now I'm not going to change, we're not going to do that. Okay, so the only way the velocity can change is, well, the direction is not going to change. We're only going to change the magnitude of the velocity. Okay, so we're keeping them simple. All right, so now let me ask you this. Okay. Is this, does this have acceleration?
Yes.
Angular acceleration?
It's slowing down.
Oh, okay. So let's assume it's frictionless. No, then it's not, right? Okay. How about now? Yeah, okay. All right, so it was slowing down. So now let's see if you guys can figure out this direction of the acceleration. Okay, so here's the initial velocity of this guy. There's the final velocity of this guy. How did the velocity change? Did the velocity change?
Yes.
Okay. And what about the velocity changed?
The magnitude of it increased.
The magnitude increased. Very good. And what direction was the acceleration? In the same direction as the velocity. Okay. All right. So I'm setting you up. I'm going to ask you a related question for rotational motion. Yeah. And so now that you have helped me out, okay, the magnitude decreased and the acceleration was in the opposite direction. Okay. All right. Let's come back to this. Is it accelerating? No. What is the direction of the velocity? Angular velocity. You use your right hand, point your fingers in this direction, and that's the direction of the velocity. Okay? All right, is it accelerating? What is the direction of the acceleration? Same direction as the velocity. Okay? And if it's slowing down, the acceleration is in the opposite direction. Okay? All right. So again, whenever you're doing this angular motion, have the linear motion in the back of your mind. All right, so angular acceleration, you are accelerating anytime your velocity changes. Okay, so angular acceleration is denoted by alpha, and its rate of change of angular velocity. Okay, we're not writing vectors because you got to keep in your mind. You got to keep the direction acceleration. Okay, it's along the axis, and to figure out which direction of the axis it is, you use your right hand. Yeah. So angular acceleration denoted by alpha is d omega by dt. Okay. So again, sign convention, alpha acceleration is pointing in the same direction as the angular velocity if the magnitude is increasing. And it's pointing in the opposite direction if it's slowing down, okay, if the magnitude of the angular velocity is decreasing. So if angular speed is increasing, then the acceleration vector points in the same direction as the velocity vector. Okay. Now, it turns out that you can do a vector representation. Okay, so what this is showing you is the following. Okay. So let's imagine a disk here. And if the, okay, so this diagram is not correct. Okay, I need to change the diagram. Okay. All right. So let's say I rotate this by a small angle. I rotate this object by a small angle. What was the distance through which this moved? This moved through a distance ds. Okay, so, and you see the further out you are from the axis, the more it moves for the same small angle. Okay, so that's what this formula is giving you. And you don't have to, we won't use this too often. That's the small displacement that a point that was r distance from the axis of rotation, and when theta was the angle through which this rotated. Okay, so that's what this is showing you. Okay, so this should be d theta. Okay, and this is the infinitesimal displacement that that point went through. So this should be ds. Okay, the point r away from the axis of rotation. Okay, so this formula is valid for infinitesimal rotations. So this is the infinitesimal displacement of a point that when the object rotated through d theta for a point that was r from the axis of rotation. Again, the instantaneous, so when the object is rotating, the velocity of this particle, okay. So when the object is rotating, the instantaneous velocity of that point is omega, r cross omega. Okay? Is the instantaneous velocity is omega cross r. Okay, omega cross r is the instantaneous velocity. Okay. Okay. Again, we won't be using those formulas too much. Tangential acceleration. Anybody remember what tangential acceleration is? Okay, so let's go back. Okay, let's say you're driving on a circular road. Okay. You're going at constant speed. Your speed is constant. Are you accelerating?
Yes.
Why are you accelerating?
It's changing direction.
Very good. Okay, so and you're accelerating, and you have, even though your speed is constant, the direction is changing. Okay. And so you're accelerating, and you have centripetal acceleration, which is equal to your speed squared divided by the radius of the circle. Okay. Now, so you have centripetal acceleration even if you're going at constant speed. Let's say now you drive faster. Your speed changes. Is that possible? Of course. You can go on a circular road and your speed can increase. Okay. When your speed also is increasing, now you have tangential acceleration. Okay. Why did we call it tangential acceleration?
The slope at that point is the velocity.
I'll say that again.
The slope at that point is, or the slope of that line when it touches like the path is the velocity. Or something like that.
If we call it tangential acceleration because it is tangent to the path. That's all. It's as simple as that. Okay. So when the magnitude of the velocity changes, that component of the acceleration is tangent to the path. Okay. So your path can be anything you want. Okay. So let's write that down. Okay. So when the magnitude of velocity changes, that component of the acceleration is tangent to the path. And so we call it tangential acceleration, okay? All right, so it turns out that, okay, so let's get back to the wheel. Yeah. Now I'm going to, as I'm spinning it faster, the speed of each point is changing, and that tangential acceleration, it has centripetal acceleration. The tangential acceleration is given by that formula. Okay? So the tangential acceleration, that point has centripetal acceleration as well, but the tangential acceleration is given by alpha, the angular acceleration of the wheel, times how far that point is from the axis of rotation. Okay. So it's this cross product. The tangential acceleration is angular acceleration crossed with the vector from the axis of rotation. Again, these three vectors are mutually perpendicular. Yeah. All right, now what we're going to do is the following. In the next few slides, we'll show you the following. Okay, so we had looked at one-dimensional motion, okay, and when the acceleration was constant, okay, you saw that you had these equations. This was the final velocity was the initial velocity plus acceleration times time. X final minus x initial was equal to initial velocity times time plus 1/2 at square, and these equations were valid when acceleration was constant. V square was equal to x final minus x initial. Yep. What we'll do is we'll derive, well, we won't derive it, but we'll show it to you. We'll have the exact same corresponding equations. The corresponding equation will be omega final equal to omega initial plus alpha times t. Okay. For constant angular acceleration. Okay. This equation will be replaced by theta final is theta initial equal to omega initial times t plus 1/2 alpha times t squared. Yep. Can anybody help me out with this, guys? What will be the replacement for this guy? What will be the corresponding equation for this?
Omega final scale equals omega initial scale plus 2 alpha theta final minus theta initial.
Very good. Okay. So those will be the kinematic equations for rotational motion. And when will they be valid?
Constant.
When alpha is constant. Okay. All right, so over the next two chapters, here's what you're going to study. You replace x by theta. You replace v by omega. You replace a by alpha. You replace force by torques. You replace mass by moment of inertia. Okay. You replace linear momentum, which was equal to m times v, by something called angular momentum, which will be I times alpha, I times omega. Okay. And every equation that you've studied in the past, you'll get the corresponding equation for rotational motion. Okay. So that's all you need to do. Okay. All right, so let's go toward that. So again, I'm not going to derive this, so here is, this is how the derivation goes, but alpha, the angular acceleration, is time rate of change of angular velocity. So here's an equation, you can integrate both sides, and we're dealing with constant acceleration, we're studying constant accelerated motion, so this comes out. So this will be alpha dt, which is alpha times t final minus t initial. And so, and this is omega initial to final, which is omega final minus omega initial, equal to alpha times t final minus t initial. We'll call t initial 0, and then we'll just label t final as t. So omega final minus omega initial equal to alpha times t. Omega final equal to omega initial plus alpha times t. Okay. Again, in this derivation, remember we assumed alpha was constant, so we could pull that out. Okay. So here is the first equation. Okay, first kinematic equation. Angular velocity, final angular velocity is initial angular velocity plus alpha times t. That is, angular velocity is a linear function of time. Yep. Angular velocity linearly increases with time. Yep. So similarly, you can do the following. Again, use this equation, do the integral, and then substitute for omega. Okay. Angular displacement, that is final angular position minus initial angular position, is initial angular velocity times time plus 1/2 alpha times t squared. And this is the parallel of this equation. Okay. So this was linear displacement was equal to initial velocity times time plus 1/2 at squared. That is got replaced by this. Okay. Angular displacement is initial angular velocity times time plus 1/2 at squared for 1/2 alpha t squared. Okay. And then using a little algebra in between these two equations, you can show this. So this is final angular velocity square is equal to initial angular velocity square plus 2 alpha angular acceleration times the angular displacement. Okay. Again, that is the parallel of v square equal to v initial square plus 2a x final minus x initial. Okay. And this is the angular displacement is average angular velocity times time. Okay. All right, so here are the equations summarized. Okay. These equations are valid under constant acceleration. Okay, so constant linear acceleration, constant a and alpha. Okay, constant a and alpha. Okay. So here are the equations you studied. Velocity as a function of time, angular velocity as a function of time. Yeah. So angular velocity is a linear function of time. Your velocity is a linear function of time. Here is the position as a function of time. Okay, so here's the final position as a function of time. Final angular position as a function of time. Okay. Here's the velocity as a function of displacement or as a function of position. Okay? Velocity as a function of position, angular velocity as a function of angular position. Okay? And again, this is average angular velocity, average linear velocity. Okay, okay, again, so the idea was Here's what's pretty neat or amazing. This linear motion in one dimension, looked like it was not at all related to this rotational motion of a rigid object about a fixed axis. But it turns out that they are cousins. Okay? The formulas describing them are very similar, I guess, describing those motion. And that's pretty amazing. Okay. All right, now you saw that as this object rotates, the closer, there's the axis of rotation coming out of the plane of the paper. The closer you are, the slower you're moving. And points on the axis, how fast are they moving? They're at rest, okay? So the further out you are, the faster you're moving. So this formula, what it does is it gives you the speed of a point that is distance r from the axis of rotation. Okay, so the velocity of this guy at a distance r from the axis of rotation is v is r times omega. Now in these formulas that relate linear quantities to angular quantities, these angular quantities have to be in radians and radians per second. So this velocity is, this angular velocity is in radians per second. Okay? So if this is in meters, then this will come out in meters per second. Okay? So let me do this. So omega is in radians per second. And if r is in meters, then the velocity comes out in meters per second. What happened to the radians?
It's a unitless dimension.
Very good. Okay. So radian was just a label, remember? It's dimensionless. So here's what I want you to remember. In formula relating linear and angular quantities, angles are measured in radians. Okay. Okay, so here's another formula. Tangential acceleration is r times alpha. So tangential acceleration, what does tangential acceleration tell you? When do you have tangential acceleration?
When the direction changes and the magnitude of the velocity changes.
Oh, you got it half right. When the direction changes, what kind of acceleration do you have?
Centrifugal.
Very good. So you have radial acceleration. When magnitude changes, you have tangential acceleration. And why is it called tangential acceleration? Because it's tangent to the path. And radial acceleration, that's perpendicular to the path. Okay? So this is an acceleration that arises because change in direction and it's perpendicular to the path. This is the acceleration that arises because of change in magnitude and it's tangent to the path. Okay? All right. All right, so the tangential acceleration is r times the angular acceleration. Okay. Again, here's a linear quantity being related to an angular quantity. And so what are the units for this guy? For alpha. In this formula, the only units this is
Radians per second.
very good. So the only unit it can go is radians per second squared. Okay? Well, the angular measure has to be in radians. It can be radians per r square or radians per meter square, but the angle has to be in radians. Okay. Here's centripetal acceleration, okay, which is r times omega square, v square by r square. Again, this has to be in radians per whatever second or. Okay. All right. So the message is: anytime you have a formula that relates linear quantities to angular quantities, the angular measure has to be in radians. Okay. Okay. What did we say? In rotational motion, mass gets replaced by what?
Impulse.
No, moment of inertia. Okay. Okay. So we are going to introduce moment of inertia to you. Okay. All right. So let's look at a rotating object. Okay, here is the axis of rotation. Okay. And as this guy rotates, when an object is moving, what kind of energy does it have? It has kinetic energy. Okay. All right. So here, the problem with this, so when you were driving your car, this was easy because every point on the car had the same velocity, and so the kinetic energy was defined as one half the mass of the entire car times v squared. Well, when this guy is rotating, the problem is the further out you are, the greater your velocity. Essentially, every point has a different velocity. So how do we calculate its kinetic energy? That's the problem. Well, you guys are calculus experts, so what you do is you break this guy into little pieces. What is the kinetic energy of this guy? It's the kinetic energy of this guy plus the kinetic energy of this guy plus the kinetic energy of this guy plus. And you guys know infinite sums. No big deal. All right, so the kinetic energy of the entire object is the kinetic energy of the little pieces, and then you sum over all the little pieces. Well, this guy is a little hard to do, but let's do a little trick. Well, this velocity is related to the angular velocity, to this guy. Okay? So that velocity is VI is RI, how far you are from the axis, times angular velocity. Angular velocity is the same for every point on the object. Okay? And that's what we did. We replaced it by I, omega. And so this omega square, which is constant, comes out of the summation sign. Half comes out of the summation sign. And then you have this guy, the mass of each particle times how far you're from the axis squared. Now again, this sum is hard to do, but for some symmetric objects, this can be done, and they actually do it for you, and they give it to you on tables. And this guy we call the moment of inertia. Okay, so I is defined as each little piece of the object times the distance of that piece squared from the axis of rotation. All right, so I'm going to ask you a question. Might be a little tricky, well, but think about it before you shoot. Let's say you guys have all had pizza. You guys have seen those guys throw the pizza dough and stuff. So let's say here's the axis, here's the pizza dough. Now as you're flattening out the pizza, does the mass of that thing change?
No.
No. Did the moment of inertia change about that axis? What happened to it?
Because the radius became more just
Yes, so each little pieces went further out. Okay, so the moment of inertia will have increased. Okay, did you guys understand that? Okay, so even though now there are smaller masses, but it's spread over a larger distance and the moment of inertia increased. Okay, so you take the same object and put the mass further from the axis of rotation, your moment of inertia increases. Okay, all right. So now what we're going to show you is the mass of an object is one unique number, but the moment of inertia, an object can have infinite moment of inertias. Okay? It just depends on what axis you're calculating the moment of inertia. Okay? So here's an object. What we're going to do is we're going to spin it about this axis. So we're going to calculate the moment of inertia about that axis. And here's the formula for the moment of inertia. It's each mass, component mass, times the distance of that component from the axis of rotation. Okay, here's the axis. This mass is right on the axis, so the distance from the axis is 0. So these are sort of point particles. Okay. This guy, that's the distance from the axis of rotation. This guy, that's the distance from the axis of rotation. So the moment of inertia about that axis is that plus this, and 0 for these two guys. So the moment of inertia is 2 ma squared. Now we'll take the same object and calculate the moment of inertia about this axis, okay, coming out of the plane of the paper. And it turns out that it's, again, those two terms, ma square plus ma square plus little mb square plus little mb square. So the moment of inertia of this guy, of the same object about this axis, is different than that. It's greater for this axis than the other axis. So it turns out that you learned torque is moment of inertia times alpha. There's Newton's second law. So to rotate this object about this axis will be harder than to rotate the same object about this axis. Okay? So again, how many different axes can you calculate the moment of inertia of this object about?
Infinite.
Infinitely many. You can calculate it about any axis you want. Okay? So an object, a given object can have infinite number of moments of inertia. It just depends on what axis you're calculating. Okay, the moment of inertia is an important quantity, and so if you wanted to calculate the moment of inertia of a continuous object, this formula gets replaced by an integral, by a triple integral. Okay, so the moment of inertia is the mass of this little piece times the distance square, and then you integrate over all the little pieces. Okay. Of course, if the density is uniform, the mass is the density of the material times the volume element, the volume of that mass. And so that's a triple integral. And those triple integrals are done for you for certain standard shapes. And they calculate these moments of inertia. Okay, you don't have to do that. Okay, so here's a table. And these guys are important enough that you have to do them. So here's a solid sphere. So for instance, a bowling ball, the moment of inertia about that axis is 2/5 mr squared. M is the mass of the object and r is the radius of the object. For a ring, the moment of inertia about that axis is just mr squared, and so on. Okay. The moment of inertia of a rectangular slab about that axis is that. I is ma squared b squared by 12. The moment of inertia of a rod about that axis is 1/3 ml squared. And for the same rod about that axis is about the same axis is 1/12 ml squared. Okay? So about the end it's 1/3 ml squared, and about the center it's 1/12 ml squared. So this moment of inertia is 4 times greater than that moment of inertia. Okay? All right. Now, notice most of these moments of inertia are given through an axis passing through the center of mass, except for this one. Okay. All these moments of inertia are given for an axis passing through the center of mass. Why is that? Because that was the integral they could do easily. What if you wanted, for some application, you wanted to find the moment of inertia about this axis? Well, that integral is harder to do. But this parallel axis theorem helps us out. Okay? And what this parallel axis theorem says is, if you know the moment of inertia about a center of mass for an object, like the name says, you can calculate the moment of inertia about any parallel axis using this theorem. Okay, and what it says is the moment of inertia about this axis, the moment of inertia about that axis is the moment of inertia about the center of mass axis, about an axis passing through the center of mass, times the mass of this object, times this distance squared. Okay. So, if you know the moment of inertia about an axis passing through the center of mass, you can calculate the moment of inertia about any other parallel axis. Okay? It's just that moment of inertia, the center of mass moment of inertia times plus md squared. Okay? All right, guys. So what we'll do is we'll